One light year is about 9.46 trillion kilometers. Write that number down if you like, though I warn you it will mean nothing to you. Numbers of that scale don't mean anything to human beings, not really. What I want to do is make it mean something, not by shrinking the number, which would be dishonest, but by standing inside it and showing you its true shape. Because when you understand what that distance actually demands of physics, something shifts. And it doesn't shift in a comfortable direction. So, how long does it take to travel 1 light year? The naive answer, the answer you'd get from a high school textbook or from a science documentary that doesn't want to make you uncomfortable, is this: divide the distance by your speed, and out comes your travel time. Simple arithmetic, Newtonian, clean. And for the purposes of everyday life, cars, trains, aircraft, perfectly adequate. But we are not talking about a car trip. We are talking about crossing 9.46 trillion kilometers, and the moment you seriously try to do that, the moment you ask what physics actually permits, what the universe actually allows, the arithmetic stops being simple. It stops being Newtonian. And the comfortable picture begins to crack in ways that are not cosmetic. They are structural. The crack goes all the way down to the foundation. Let me start with what we actually have. Humanity has launched objects into space for roughly 60 years. The fastest of them, Voyager 1, which departed in 1977 and is now the most distant human-made object in existence, travels at approximately 17 kilometers per second. That sounds impressive. 17 kilometers every second. London to Edinburgh in under 40 seconds. Across the Atlantic in under 7 minutes. Fast enough to feel, intuitively, like it ought to get somewhere significant in a reasonable amount of time. It does not. At 17 kilometers per second, to cross 1 light year, 9.46 trillion kilometers, would take approximately 17,500 years, not centuries, not millennia in the comfortable abstract sense, 17,500 years. The entire span of recorded human history is roughly 5,000 years. We are talking about 3.5 times that, before the wheel, before agriculture, before the first city was built on the banks of the Euphrates. That is the scale of time you are looking at if you want to travel 1 light year using the best propulsion technology humanity has actually built and launched. That is not an engineering problem. That is a statement about the relationship between human timescales and cosmic distances. And you need to feel that before we go any further, because everything else I am going to say depends on you having genuinely absorbed it. Good. Now let's break it. The obvious response, the response that every serious discussion of interstellar travel reaches within about 5 minutes, is to go faster. If 17 kilometers per second is too slow, build something faster. And this is not a stupid response. It is the correct instinct. The question is what faster actually costs you, physically, as you pursue it. Because the universe has opinions about speed that become very loud as you approach certain limits, and those opinions are not negotiable. Consider what it takes to accelerate a spacecraft. You need energy. The faster you want to go, the more energy you need. For low speeds, low relative to the speed of light, the relationship is approximately what Newton told us. Kinetic energy equals 1/2 times mass times velocity squared. Double the speed, quadruple the energy. Manageable. Painful, but manageable in principle. But as your velocity approaches the speed of light, and for interstellar travel within any human-relevant time frame, the Newtonian formula fails. It fails, not because Newton was careless, but because Newton didn't know about relativity. The correct formula, the one Einstein gave us in 1905, tells you that the energy required to accelerate a mass to a given fraction of the speed of light grows not as velocity squared, but in a way that diverges, that goes to infinity as velocity approaches the speed of light itself. There is no finite amount of energy that will push a material object to light speed. None. This is not an engineering limitation. It is a law of physics, built into the structure of spacetime itself. But here is where it gets strange. Because relativistic travel at a significant fraction of the speed of light, does not simply make the journey faster in the obvious sense. It does something far more radical. It changes the geometry of time. This is not metaphor. This is not poetic language dressed up as physics. This is a measured, experimentally verified, mathematically precise fact about how the universe is built. When you move at high velocity relative to some reference frame, time for you on your spacecraft, in your bones, in your biochemistry passes more slowly than time for observers who are stationary relative to you. This is called time dilation, and it is real in the most brutal, unambiguous sense of the word real. We measure it. We have measured it with atomic clocks on aircraft. We correct for it in GPS satellites every single day, because if we didn't correct for it, your navigation would drift by kilometers within hours. This is not theoretical. This is engineering. So what does time dilation mean for interstellar travel? It means that the question, how long does it take to travel 1 light year, does not have a single answer. It has at least 2 answers, depending on whose clock you are consulting. And those 2 answers can differ not by a small correction, not by a few percent, but by orders of magnitude. Here is a thought experiment that I want you to hold on to. Imagine a spacecraft that can accelerate continuously at 1 g, that is, at the same rate as Earth's gravitational pull. This is a convenient choice because human beings can tolerate 1 g indefinitely. It is also physically interesting because, as Einstein showed in the equivalence principle, you cannot locally distinguish between being in a gravitational field and being in an accelerating rocket. But that is a separate lecture. For now, 1 g of continuous acceleration. At 1 g of continuous acceleration, you reach approximately 77% of the speed of light after about 1 year of ship time. After 2 years of ship time, you are near 95% of light speed. After about 3.5 years of ship time, you are sufficiently close to light speed that time dilation becomes dramatic. You are moving through space at a pace that, from the outside, looks nearly as fast as light, but from inside the ship, time is passing at a fraction of the rate it passes outside. Now, 1 light year, traveled at close to light speed, takes, from Earth's perspective, just over 1 year. But from the traveler's perspective, because of time dilation, the elapsed time is less, considerably less, if the speed is high enough. If you are traveling at 99.9% of the speed of light, the Lorentz factor, the factor by which your time is dilated, is approximately 22, meaning for every 22 years that pass on Earth, roughly 1 year passes on the ship. At that speed, crossing 1 light year takes Earth time just over 1 year, but ship time closer to about 2 to 3 weeks. Does that sound like a solution? I want you to resist that conclusion for a moment, because there is a cost. There is always a cost, and the cost here is the energy. To accelerate a spacecraft of even modest mass, let us say 10,000 kilograms, a small crude vehicle, stripped of everything unnecessary, to 99.9% of light speed, requires an amount of energy that I am going to make concrete for you, because the abstract number is meaningless. The kinetic energy of a 10,000 kilogram spacecraft at 99.9% of light speed is approximately 2 times 10 to the power of 21 joules. For comparison, the total energy output of all of humanity in a single year, every power plant, every car, every fire, every metabolic process, is roughly 5 times 10 to the power of 20 joules. So we are talking about roughly 4 times the total annual energy consumption of our entire civilization, just to get one small spacecraft up to that speed. And that is assuming perfect efficiency, perfect conversion of energy into thrust, no losses, no waste. Nothing in real engineering is perfectly efficient. Nothing. And there is another cost, which is subtler and in some ways more disturbing. When you travel at 99.9% of light speed, you do not arrive back home to find that the same amount of time has passed as you experienced. You arrive to find that far more time has passed outside. If you take a journey of what feels to you like 2 years out to some destination, 1 light year away and back, you return home to find that something closer to 44 years have elapsed on Earth. Your friends are old or dead. Your children have grown up without you. The institutions you knew have changed or vanished. This is not a story about loneliness, though it is that too. This is a statement about the structure of spacetime. The universe does not have a single universal clock. Time is not a river flowing at the same rate everywhere. It is a dimension of a 4-dimensional manifold spacetime, and your path through that manifold determines how much of it you traverse. Move through space quickly, and you traverse less time. Stay still, and you traverse more. These are not the same journey, and they cannot be made the same journey, and anyone who tells you otherwise is confusing the map for the territory. This is the point where I want to say something about my own history with these ideas, because it is relevant, and because I think honesty about how understanding actually develops is more useful than the sanitized version. When I was a graduate student, this is the late 1950s, Cambridge, a world that feels almost geological in its distance from this room, the implications of special relativity for space travel were well understood mathematically. The Lorentz transformations had been around for 50 years. Time dilation was established, but there was still, in many quarters, a kind of psychological resistance to taking these implications fully seriously. People could do the calculation and get the right number, and still somehow not quite believe that the universe was actually built that way. That time really did pass differently for moving observers. That simultaneity really was relative. That there was no fact of the matter, independent of reference frame, about whether two events happened at the same time. I had that resistance myself, in a mild form. Not to the mathematics was clear, but to the physical reality of it. There is a gap between being able to solve the equations and genuinely absorbing what the equations are telling you about the world. I think it took me until my work on singularities and black holes, the work I did in the early 1960s, developing the singularity theorems before I genuinely stopped treating relativity as a mathematical tool and started treating it as a description of reality. And that shift changed how I thought about everything. Because once you genuinely accept that spacetime is a four-dimensional manifold with a pseudo-Riemannian metric, once you stop thinking of time as a backdrop against which events happen and start thinking of it as a dimension that is geometrically intertwined with space, the question, how long does it take to travel 1 light year, becomes not one question, but a family of questions. And the family is rich and strange, and does not have the tidy single answer that common sense expects. Now here is where it gets stranger still. I have been talking about special relativity, Einstein's 1905 theory, which describes the behavior of objects moving at constant velocity relative to each other in flat spacetime. But the universe is not flat. The universe is curved. Mass curves spacetime, as Einstein showed in his 1915 general theory of relativity. And that curvature has implications for interstellar travel that go well beyond what special relativity alone tells us. The most dramatic of these implications, and the one that has generated the most confused popular discussion, is the possibility of what are called space-time shortcuts, wormholes, regions where space-time is so dramatically curved that two points which are far apart in the ordinary sense might be connected by a path that is geometrically short. A tunnel through the fabric of space-time itself. The mathematics of wormholes is not fictional. General relativity admits solutions, exact, rigorous solutions to Einstein's field equations that describe wormhole geometries. Kip Thorne and his colleagues showed in the late 1980s that traversable wormholes are at least mathematically consistent structures. The paper is real. The equations are real. The question is, whether the physics is real, whether the universe actually instantiates such things, and if so, whether they can be used. And here I have to be genuinely honest with you, in the way that I think is the only defensible posture for a physicist. I do not know. Nobody knows. And I am not using nobody knows as a polite way of saying it is probably impossible. I am using it as a literal statement of our current epistemic position. To maintain a traversable wormhole, you need what is called exotic matter with negative energy density. We know that quantum field theory permits states with locally negative energy density through effects like the Casimir effect. Whether that permission extends to the macroscopic quantities needed to hold open a wormhole throat, whether the quantum inequalities that constrain negative energy allow it, is a question that is genuinely open. Not rhetorically open, actually open. People are working on it, including people whose work I respect enormously. What I will say is this: the gap between the mathematics permits it, and the physics allows it, and the engineering can achieve it, is not a gap you can hand-wave across. Each of those steps requires real work, real physics, real experimental verification. And we are, at present, at step 1, the mathematics. We have not yet cleared step 2, let alone step 3. But let me not dismiss this too quickly, because there is something important in the fact that general relativity, which is our best theory of gravity, confirmed to extraordinary precision by everything from the perihelion of Mercury to gravitational wave detection, does not simply prohibit wormholes. It does not rule them out the way quantum mechanics rules out, say, measuring both position and momentum to arbitrary precision simultaneously. That is a genuine, hard prohibition. Wormholes exist in a different category. Theoretically possible, physically uncertain, engineeringly fantastical. That is not nothing. It is not a license for optimism, but it is not a door slammed shut either. Now, I want to return to a question that I promised to take seriously, and that most discussions of interstellar travel quietly skip over, because the answer is so uncomfortable. Suppose you could travel at, say, 10% of the speed of light. Slow, by relativistic standards, time dilation effects are modest, roughly 0.5%. Earth time and ship time are nearly identical. 1 light year would take you 10 years. A human lifetime might get you a few light years. The nearest star system, Alpha Centauri, is 4.37 light years away, 44 years at 10% light speed. A long mission, but not an impossible one in terms of human lifespan. The energy cost at 10% light speed is significantly less than at 99.9%. For our 10,000 kilogram spacecraft, roughly 4.5 times 10 to the 19 joules. Still an enormous number, about 1/10 of humanity's total annual energy consumption, but dramatically less than the relativistic case. And the propulsion concepts that might achieve 10% light speed are not entirely fanciful. Laser sails, where a powerful laser array accelerates a lightweight craft over years. Nuclear pulse propulsion, which was actually seriously studied in the 1950s under the name Project Orion. Fusion drives. None of these are ready. All of them have severe engineering obstacles. But none of them violate known physics. The physicist, Robert Bussard, proposed in 1960 what became known as the Bussard ramjet, a spacecraft with a vast magnetic funnel that scooped interstellar hydrogen as it traveled, using it as fusion fuel. The appeal was obvious: you don't have to carry your fuel. The interstellar medium is your fuel. Bussard calculated that such a ramjet could, in principle, accelerate indefinitely, approaching light speed over time. Later analysis showed serious problems with the concept the interstellar medium is too sparse. The drag from the scoop may exceed the thrust from the fusion. The proton-proton fusion cycle is too slow and energetically inefficient. The idea, as originally stated, probably doesn't work, but the impulse behind it find a way to sidestep the tyranny of the rocket equation is exactly the right impulse. The rocket equation, Tsiolkovsky's equation, tells you that the mass of fuel required to accelerate a rocket grows exponentially with the velocity change you want to achieve. Exponentially. For interstellar speeds, the fuel mass required by conventional rocketry is not merely impractical, it exceeds the mass of the observable universe by factors that make the comparison absurd. The rocket equation is not an obstacle to be engineered around. It is a wall. You need a fundamentally different approach. This is, I think, the honest summary of where we actually are. The distance of 1 light year is not a problem of technology in the straightforward sense. It is not like building a better steam engine or inventing the transistor. It is a problem that sits at the intersection of physics, energy economics, and the hard limits imposed by the structure of spacetime itself. And those limits are not soft. They do not yield to optimism or to funding. What they might yield to, and I say this with real uncertainty, not false hope, is understanding. Not understanding we currently have. Understanding we do not yet have. Here is what I mean. There are things about space-time that we do not understand at a fundamental level. We have general relativity, which is our best theory of gravity, and it works extraordinarily well at scales from millimeters to billions of light years. We have quantum field theory, which is our best theory of matter and non-gravitational forces, and it works extraordinarily well at subatomic scales. These two theories are, at present, fundamentally incompatible. They cannot both be exactly right. At the Planck scale distances of roughly 10 to the minus 35 meters, energies of roughly 10 to the 19 GeV, both theories break down, and we do not have a replacement. This is not a secret problem being quietly solved in some back office. It is the central unsolved problem of theoretical physics. It has been the central unsolved problem of theoretical physics for nearly a century. String theory was proposed as a solution. I have been, let us say, a skeptic. Not of the mathematical ingenuity. The mathematical ingenuity is real and often impressive, but of whether it is physics, in the sense of making testable predictions about the actual world. My disagreement with many colleagues on this point has been long and sometimes heated, and I don't intend to relitigate it here. My point is different. My point is that whatever the correct theory of quantum gravity turns out to be, and I believe, for reasons I've laid out in considerable detail elsewhere, that it will involve a modification of quantum mechanics itself, not just of general relativity, whatever that theory is. It will change our picture of spacetime at the deepest level. And a changed picture of spacetime at the deepest level might reveal possibilities that our current, incomplete theories cannot see. I am not saying this as consolation. I am not saying, don't worry, future physics will solve everything. I am saying that the history of physics is full of cases where a foundational revision revealed possibilities and impossibilities that the previous theory got wrong. Classical mechanics said that atoms were stable. Classical electrodynamics said they were not an electron. Orbiting a nucleus should radiate energy and spiral inward in a fraction of a second. Both could not be right. Quantum mechanics resolved the contradiction, and in doing so revealed that the structure of matter was utterly different from what either classical theory had imagined. Not a small correction, a fundamental restructuring. We may be in a similar position with space-time. The constraints that special and general relativity place on interstellar travel are real within those theories. But those theories are not the final word. Nobody serious thinks they are the final word. What the next word says, I genuinely do not know. And I've been thinking about this for more than 50 years. There is one more thing I want to say, and it concerns a dimension of this problem that is rarely discussed, because it requires a kind of honesty that is uncomfortable. Suppose we solve the energy problem. Suppose we find some way to achieve a significant fraction of light speed without the exponential fuel costs that make rocketry absurd. Suppose we build a ship, put people on it, send it toward Alpha Centauri at 10% light speed. They arrive after 44 years of ship time and 44 years of Earth time at this speed. The people who launched them are old or dead. The mission controllers who trained them have retired. The civilization that built the ship has changed in ways that nobody can fully predict across 44 years. Now the travelers arrive. They find what? We don't know what's there. There may be nothing of interest, by the standards of beings who traveled 44 years to reach it. Or there may be something extraordinary, but they can't report back in real time. Radio signals travel at light speed. A message from Alpha Centauri takes 4.37 years to reach Earth. An answer takes another 4.37 years to return. Any real-time conversation is impossible. Any real-time guidance from Earth is impossible. The travelers are, in the most literal sense, on their own. And when they come back, if they come back, after another 44 years of travel, they return to a civilization that is 88 years older than the one that sent them, 3 or 4 generations. The people who knew them are gone. The culture has shifted. The technology has changed. They return as strangers. This is not a reason not to go. I am not making an argument against interstellar travel on the grounds that it's socially disruptive. I am making a point about what interstellar travel actually is, physically and humanly. It is not like crossing an ocean. It is not like going to Antarctica and coming back. It is a one-way journey into deep time, disguised as a voyage through space. The light year is not just a measure of distance. It is a measure of the degree to which the traveler becomes disconnected from the civilization that produced them irreversibly, permanently, in ways that cannot be undone by any amount of communication technology. The speed of light is not just a speed limit. It is the pace at which causality propagates. It is the rate at which information, any information, all information, can travel through the universe. And that pace, combined with the size of the universe, means that the universe is structured in a way that isolates its parts from each other on timescales that dwarf human history. We are not just far from the stars in the way that we are far from the other side of the Earth. We are causally isolated from them in a way that is woven into the geometry of space-time itself. That isolation is, I think, the deepest answer to the question of how long it takes to travel 1 light year. The time, 17,500 years at Voyager speed, 44 years at 10% light speed, a few weeks of ship time at 99.9% light speed with Earth time of a year is not the fundamental fact. The fundamental fact is that 1 light year represents a degree of causal separation from the rest of humanity's history that cannot be bridged by speed alone, no matter how fast you go. The universe is not simply large. It is large in a way that has consequences for what kinds of stories can be told, what kinds of connections can be maintained, what kinds of civilizations can coherently exist across interstellar distances. I have spent a great deal of my career thinking about the large-scale structure of space-time, about singularities, about conformal geometry, about what happens at the boundaries of our universe, in space and in time. And one thing that work has impressed upon me, repeatedly and forcefully, is that the universe does not care about human convenience. The speed of light is not set to a value that makes interstellar travel easy for creatures with 100-year lifespans. The distances between stars are not arranged to be crossable on timescales that feel meaningful to biological beings. The universe is what it is, and what it is happens to be extraordinarily inhospitable to the kind of rapid, connected, empire-building interstellar civilization that science fiction has trained us to expect. That might change. Fundamental physics might be revised in ways that open doors currently invisible to us. I am not in the business of claiming that something is impossible simply because we cannot currently do it. I learned better than that from the history of my own field, where claims of impossibility have a poor track record. But I am in the business of insisting that we face what we actually know without blinking. And what we actually know is this. 1 light year is a distance that exposes, with perfect clarity, the gap between the universe as it is and the universe as we might wish it to be. Every serious attempt to cross that gap by brute speed, by relativistic time dilation, by speculative space-time geometry, runs into the same hard fact. The universe is not built at our scale. It is built at its own scale, and its scale makes our entire civilization, our entire history, our entire species, something that has so far occurred entirely within a volume of space that, by cosmic standards, is essentially a single point. I find that not comforting. I find it clarifying. And clarifying, in physics as in life, is always the first step toward something better. The question is not whether we will ever reach the stars. I don't know the answer to that. Nobody does. The question is whether we are willing to understand, genuinely understand, without softening the edges, what it would actually take. Because that understanding is not pessimism. It is the beginning of real thinking. And real thinking is the only thing that has ever actually moved us forward. So the next time someone tells you that interstellar travel is just an engineering problem, that it's only a matter of time before we crack it, that the stars are waiting for us, the way America was waiting. For European ships, ask them about the rocket equation. Ask them about the Lorentz factor. Ask them where the energy comes from, and how much of it you need, and what happens to the people on Earth while the travelers are in flight, and what the travelers come home to, if they come home at all. And when they struggle with those questions, and they will struggle, if they are honest, remind them that struggling is not failure. Struggling with the right questions is the only way physics has ever actually worked. The stars are 9.46 trillion kilometers per light year away, and the universe has not apologized for that, and it is not going to.